we talked about energy, kinetic energy and potential energy that we started. And then we were looking for two types of energy, and there are a lot of options for that. So I'm going to write two. If you had other ones, this isn't everything. It could be more. You could have thought of more options, but I'm just going to give an example. When you turn on a light, our standard incandescent bulb has a wire. We put electricity across it, and it gets so hot that it glows. And it lets out that light, but it also lets out a lot of heat. So in a lamp, it'll take electricity and convert it into light and heat. Solar panels take light and convert it into electricity. And there are lots of ways that other forms of energy are involved in that. So you might have had a much richer discussion. It kind of depends on what type of solar panels they are. And then in The Simpsons, Homer works at a nuclear power plant. And the way that usually works is we have nuclear energy. So changing the energy in the nucleus releases a lot of energy. We release that. And then with that, it's converted to heat to boil water that turns a steam engine typically. So it's usually to heat. And then to mechanical energy. And then electricity. So those are some of the examples.
What about chemical energy? Like, what does that was one of the options.
Yeah, chemical energy is active with batteries. And a lot of times that has to do with the activity of metals. Metals will tend to grab electrons or release electrons. And just by lighting up the metals in the right order, you can get electrons to flow. And we will look at single replacement reactions a little bit, where we have one metal being chemically dissolved and corroded away, and then another metal will plate out. So in the chemical reactions lab, we have one example. I just have pictures for you this quarter, but it's pretty cool to see. You see the silver crystals growing on the copper wire. That's one example of chemical energy. I'm going to run through this pretty quickly. The particle spacing for gases is close packed. You can see how close they are in that solid. In a liquid, they are also close. There's a little more room. They can move around each other. They can squeeze by. And then in the gas, these are widely spaced. They're far apart. In the gas, they're not interacting with nearest neighbors at all. So for a solid, the volume is fixed, right? It's just one size. It doesn't change. So fixed volume, and the shape is also fixed too. So I think in the lecture slides, we talked about a quarter. Oh yes, of course, I've got pennies. So the penny is a certain shape and size based on the mold it was made in, and that has the year engraved on it too, right? So that doesn't change. So fixed volume and shape. In a liquid, they have a fixed volume and a variable shape, right? You could have a tall glass or a big fat glass with the same amount of the drink in it. And then with a gas, they always take the shape of the container, and that means variable volume as well. And when we think about compressing it, we're talking about using pressure to change the size. For a solid, it's not very compressible. Liquid, you know, from the people with a really keen engineering mind will say, well, you could compress it a little bit you can, but not like a gas. So we're going to say this is basically not compressible. Whereas gases are very compressible. There's so much space between the particles that they can get pushed together pretty easily. All right, does it flow? So these guys are both considered fluids. So a solid does not flow, but gases and liquids do. And here's where we're making the connection from what we did before to what we're looking at now, and that is with the energy, the relative energy in that substance. Now, we've talked a little bit about this energy scale, and this is proportional to temperature. Solid is down here, liquid is here, and the gas for the substance is always higher. So when we look at this level, the solid, how much of that lower energy is kinetic versus potential? Compared to if we look at a gas way up here, that has a higher energy, but how much of that energy is kinetic versus potential energy? For a solid, what kind of motion do those have? They vibrate in place and they have not very much kinetic energy. I'll write low. Relative kinetic energy. What about the attractive forces in that solid? Do they interact with their nearest neighbors? Yeah, they have an interaction that holds them together in that solid. So even though the overall energy is lower, right? We're looking at this level, most of that energy is potential energy. So I'll say high. It's not high total energy, because the total energy would be both of those together. Okay, now in the liquid, how much kinetic energy do they have? They can move around, so they have some. I'll write maybe medium. And then what about potential energies? Do they interact with their nearest neighbors? They have some nearest neighbor interactions. What about the gas? Does it have kinetic energy? How much? High kinetic energy. And then what about the nearest neighbors? They have no interaction. That's a 0, right? So even though they're at a higher energy, all of that high energy is kinetic energy. They have to overcome interacting favorably with their friends in order to get by themselves. And the only way that happens is with a lot of kinetic energy.
Professor, if we're talking about like the same sample of a substance, but in its solid, liquid, and gas form, because in the ALEX that we did for this, it talked about how like the total energy actually doesn't change. So like as the kinetic energy goes up, potential energy goes down, and vice versa.
Oh.
So like one sample of water, for example, and then we, the same amount, that's solid, liquid, and gas, all of those forms of it, I don't know, because like you just said that the total energy is higher in gas.
Okay, so the total energy is the sum. And the time when they're the same, we're going to do this on the next page, that's why I flipped down. The total energy is the same at a constant temperature. So that occurs during phase changes. So when you have ice and water together and they're all at 0, the ice is moving the same as the liquid, the same amount of kinetic energy, and it can pass between the liquid and solid phase. So if you add more energy, it's going to move it towards the liquid. If you remove energy, it's going to move it toward the solid.
Oh, and you're adding it in the form of heat.
Yeah, by being at room temperature.
Okay, that makes sense, yeah.
Great questions. So this is proportional to temperature, and the temperature is lower. So I'll write proportional to 0 degrees or less. This one is proportional to less than 0 degrees. This is between 100 degrees. And then this one is for temperatures greater than 100 degrees, where energy is proportional to temperature. This last line might be a little bit confusing. If it is, just let it go. We'll talk more about that. But hopefully it clarifies your question, Annie, about the total energy being relative to the other phases of matter. When they're the same, it's when they share a temperature. So we'll take a look at that next. We're going to talk about these transitions right here and right here. And those will be at the freezing and boiling points typically. To undergo a change in state from solid to liquid or liquid to gas, there must be enough thermal energy. And I think I did give this to you where the energy is 3/2 kT, where the K is Boltzmann's constant. You don't have to worry about it, but it's proportional to the temperature. So that heat in the environment has to have enough energy to overcome the attractions between the nearest neighbors, between those particles. So it's like the particles want to be with their friends. They want to be close, surrounded by their friends. So at what point do they have enough energy from the heat, enough kinetic energy, that they can move, that they can get away from their nearest neighbors because they have too much energy? We talk about those nearest neighbor interactions. Those are intermolecular forces, which I often write IMFs, intermolecular forces. And we'll talk about those for chapter 12. We're going to look at those too. And we could also have particles right next to each other that have chemical bonds such as ionic bonds, and we'll talk more about that in the bonding section. If we add enough heat, we can cause something to change phase, to go from, we can melt those ice cubes or we can boil the water. And during that phase change, the temperature is not changing. All of the added energy is going into the kinetic energy of the molecules, so that liquid cannot get hotter because it has collisions with the solid and it transfers its energy to the solid, and the solid starts moving faster until it becomes a liquid. So you can only raise the temperature of the liquid once the solid is all gone. And so let's take a look at what that looks like in this heating and cooling curve for water. So we're going to talk about a block of ice, and then we're going to heat it all the way into steam. So on here we have our temperature. We'll think in degrees Celsius, but when we're calculating, it has to be in Kelvin. And so let's talk about water. What are the important temperatures to write on there?
0 and 100.
That's right. Perfect. 0 degrees C, that's the freezing point. 100 degrees C is the boiling point. We're going to take our ice, right? We have some ice down here. Oh, and the x-axis is heat added. This is going to be added at a constant rate. So we'll just put it on a Bunsen burner or a hot plate, and we'll keep the setting constant. So over time, the same amount of heat is added. When you look at it like this, you can almost think of it as time, except that you could take away the heat and it would be like moving in reverse, right? So this is the heat added by just a constant rate. So we're going to start at -4, and as I add heat, the temperature is going to go up. Those particles are going to vibrate faster and faster. And when we get to 0, any energy that we add is going to go into melting that ice. So the temperature does not change. What's present in this flat line area where there's no change in temperature? That part has ice plus water. We're going to keep adding heat, and that's going to cause the kinetic energy. All that thermal energy is going to make the particles move faster and faster, and they're going to spread it out in the whole sample. So one might be going really fast, but then it collides with another water molecule, and that one speeds up, and the fast one slows down. So they all share that energy, and the temperature goes up until we reach the boiling point. Now at that point, we keep adding heat, but there's so much energy, so much kinetic energy in the water that we add more kinetic energy, it escapes to the gas phase. And so that's when we're vaporizing. And that line is quite long, a lot of energy to vaporize water. So in this section, what do we have when the temperature is changing?
Water.
Okay, so we get to the boiling point of water, we keep adding heat, and that's going to vaporize it until all the water's gone. Only once all of the water is gone, then that gas can increase in temperature. And that's why steam burns are so much worse than just hot water. Okay, so in this section, what do we have? We have gas plus, or I should say steam. We'll be technical here. Now, here's one of the things we are not doing in the lab is adding up the heat. If we think about taking that ice cube from -4, and let me just say maybe here is 110 degrees C, we have to add 5 terms of heat because they're all different. The way that the particles receive the heat is different from ice, water, and steam, and the formula is different when the temperature isn't changing. So it always depends on how much stuff, how much water, what mass of water, or how many moles of water, right? We talked about moles a little bit. So I would have to calculate 5 terms. Heat, I'll call Q, and we're going to add Q, we're going to heat the ice, right? So that's that first section. Then we're going to add Q to melt the ice, and that is this section. And then we're going to add the heat to heat the water, and that'll be this section. So maybe I'll call that Q3. We'll have another term right here, Q4, and that is the Q to vaporize the water. And then we'll add that last term right here, Q to heat the steam, which is much easier than it is to vaporize the water. All right, we're not going to go a lot into the math of these just because we're short of time. We're sure everybody's on board and it's more algebra intensive. The important thing to notice is that the melting the ice and the vaporizing water, those are the phase changes. Right? So this one is solid to liquid, this one is liquid to gas, and there's no temperature change there. When we look at these ones, those ones all have a slope. So these all depend on delta T as well, because it'll take more heat. If we want to go up to 120 degrees, we're going to have to add a little more heat. That temperature dependence comes in to the pure phases. When there's two phases at the same time, there's no temperature change because all the heat is absorbed into the particle motion. That's a really important difference, and we're going to look at that on the Gizmo in lab, where they show the particle interactions, right? Sum total of 5 heat terms. Kinetic energy is the energy of motion, and it depends on the temperature. It depends on how much heat is available at a given temperature. So heat is the total energy of the particles in the system. It's the same as thermal energy, right? It flows, thermal energy flows from high temperature to low temperature. Temperature is just a measure. What do we need to know here? Temperature is a measure of the average kinetic energy of the particles in a substance. So the particles are not moving the same speed. Some are moving fast and some are moving slow, but the average is proportional to the temperature in Kelvin. The amount of thermal energy is proportional to that in Kelvin. The temperature doesn't depend on how much sample is there, right? You could have the same temperature for a small beaker as you do for a large beaker, but the total amount of energy does depend on the amount of stuff. So intensive, extensive properties like we talked about in week 1. And if you think about it, like how much energy does it take to heat a cup of water compared to a whole swimming pool? Then it's very intuitive. It's going to take a lot more energy to heat up a swimming pool. So that's what we mean. The extensive property depends on the extent of the sample. Take a look at these questions. Which has higher average kinetic energy? Which one has higher thermal energy, total thermal energy? These both have a measurement of 100 degrees. So they have that in common. What is the thing that they both share? Is it the average kinetic energy or is it the amount of thermal energy?
Kinetic energy.
Yes, thank you. Average kinetic energy is proportional to the temperature. So same temperature, same average kinetic energy. What about thermal energy? Which one has more heat associated?
B.
More water at the temperature. So the total energy is more in the larger sample.